High privilege to welcome you all to this first session of the fourth day of AICT Training and Learning Atal Academy sponsored 1 week faculty development program on antenna design, fabrication and measurement. On behalf of all the faculty members of GP Pant Institute of Engineering and Technology, I would like to welcome our today's session expert, Dr. Karimuddin Rambabu, sir, who will be delivering his session on time domain analysis of ultra wideband antennas and their near field characteristics. Kindly allow me to give a brief introduction of him before I hand over the session. Dr. Karimuddin Rambabu sir received the member of IEEE, received the PhD degree in electrical and computer engineering from the University of Victoria, Victoria, BC, Canada in 2005. He was a research member with the Institute of Infocom Research, Singapore from 2005 to 2007. Since 2007, he has been assistant professor with the Department of Electrical and Computer Engineering, University of Alberta, Edmonton, AB, Canada, where he is currently a professor. He is currently involved in industrial and biomedical imaging, vital sign monitoring, and biopsy needle guiding using ultra-wideband radar systems. His current research interests include the design and development of ultra-wideband technology and components and radar systems for various applications. Dr. Rambabu was a recipient of the Andy Farquharson Award for Excellence in Graduate and Student Teaching from the University of Victoria in 2003 and the Governor General's Gold Medal for the PhD research in 2005. He also serves as an associate editor for the IET Microwaves Antennas Propagation. So we are glad to have Dr. K. Rambabu sir for this FDP session. Thank you so much, sir. And I would hand over the session to you now. Over to you, sir.
Thank you, Rishi. Thank you. Okay, good morning, everyone. I'm Rambabu Karamudi from the University of Alberta, Canada. Today, I'm going to share our group research on UWB technologies, especially on UWB antennas, time domain analysis of UWB antennas and near field characteristics and far field characteristics of the radiated pulse. Quite often, you have seen so many antennas analysis using frequency domain. However, ultra-wideband antennas are meant for radiating sharp electromagnetic pulses. It means it is going to have huge spectrum in the pulse. So we will directly deal in terms of time domain analysis for this UWB antennas. In the literature, quite often we are not going to see that. At the end of the talk, I would like to share my perspective on future time domain systems or UWB systems and UWB antenna research in special. Okay, before we go into the today's talk, I would like to introduce my university a little bit more so that we'll have a good connection with each other. Where we are, Edmonton is located in the province of, first let me introduce the university. Our University of Alberta is located in Edmonton. Edmonton is in the province of Alberta. You could see in this picture, we have a river in between, which is called North Saskatchewan River. And the north side of that is the city downtown. This skyline you are seeing here, this is high rises or downtown. And the south side of this river is the university. This is the region, university region. Quite often you won't see such big universities situated so close to the downtown. But University of Alberta is very close to the downtown. One more thing about this Edmonton, right now my local time is 9:04 p.m. and still we are seeing the sun here. Unfortunately, I'm not able to show you that because of this presentation mode. And to tell you, minus 40 degrees is quite common for us. And especially this year, our summer is also super hot. We have seen plus 38 degrees Celsius. Okay, if I zoom on to more onto the university, this is the north campus of the university. Our engineering, this region is the engineering region, and this region is the medical, this side is arts, and this region is science. Okay, this is our building, Faculty of Engineering building. This building is home for almost 1,000 people, including faculty and students. Okay, now we will go into today's talk, ultra-wideband technologies. First of all, why do we need ultra-wideband technologies? We know that narrowband communications or radar systems are there since so long. It is generating narrowband signals is simple. Using RLC circuits, we can produce these signals. And the beautiful option we have is resonance effect. Using resonance effect, we could achieve the best performance, be it antenna, be it communication system or radar or anything. Even though we have these kind of great features, still we are looking for ultra wideband technologies just for one reason. We want more information. Our systems need to support high data rates. For that reason, we are selecting ultra wideband technologies. If we want now in communication, 5G is knocking on our doors. We are expecting to receive gigabits of data rates. Same thing in the radar domain as well. Perhaps you all might have heard microwave imaging for biomedical application, where people are expecting 2 millimeter image resolution. To achieve 2 millimeter microwave image resolution, we need almost 10 gigahertz of bandwidth. So the future, wherever we want high data rate communication or high resolution imaging, we need ultra wideband technologies. Of course, antenna is the primary component of ultra wideband for any system for that matter. Okay, before we entered, we will look into some of the UWB applications. Ultra-wideband systems are meant for short-range communication, high data rate communication. For example, IEEE 802.11ax is expecting 10 gigabits of data rates. Today, some systems are delivering 2 gigabits per second. Perhaps you might have heard recent Japanese announcement of terabits of data per second using internet, means optical cables, not wireless. So as of today, this wireless expected data rate is going to be 10 gigabits per second. I believe in near future, we are going to see these kind of data rates. Whereas in the radar application side, biomedical and industrial imaging application and Internet of Things. Recently, Internet of Things are becoming so popular. If you have a cell phone from like iPhone 11 and above versions, we have UWB chipset inside. They will give you environmental perception. Environmental perception is the new research area which is thriving and going to thrive in near future. Using these UWB sensors, we can develop various tools and instrumentations. Why I'm talking about is what is the importance? Why somebody really need to do research in UWB antennas? What could be their future? Okay, if we see the literature, we have so many antennas already built. Sometimes ourselves will question, do we really need more designs? Don't we have enough of the antennas already designed? I'm sure many of you contributed to the literature. You have published multiple papers on UWB antennas already. If we look at them, still, do we need research? We will look into the discussion and we conclude at the end. Okay, if I focus on the primary antennas for UWB applications in the literature, we have ridge horns, TEM horns, Vivaldi antennas. Quite often we use Vivaldi antennas being a planar antennas, spiral antennas, fractals, bicones, and even I would say millions of monopole antennas have been designed already. If we see in the literature, are we characterizing these antennas for ultra wideband applications? Let's see. Whenever you see any antenna paper, there would be a design. They would be evaluating the antenna by measuring the return loss or S11 as a function of frequency to say that antenna achieved the bandwidth. Again, we will say that our gain is good and pattern stability is there over the bandwidth. Most of the time, these are the two evaluations we are providing in the literature. Sometimes we see group delay measurements as well, but rarely we will see location of the phase center or phase distortion as a function of frequency. Most of the time, we are evaluating our antennas using these 4 points: S11, gain or pattern stability, group delays. But UWB application or UWB antennas in real application needs to radiate and receive short electromagnetic pulses. Now we want to really understand how the antennas are radiating pulses. You could say that from previous studies, frequency domain analysis has been done. Even in undergrad antennas and propagation courses, we learn through auxiliary potential functions. We find first we'll take the source currents, then define the auxiliary potentials A and F. By solving A and F, then we use again differentiation to get electric and magnetic fields. We seldom see in any literature time domain radiation concepts. Okay, now our goal is how to analyze the UWB antennas for radiated pulse shape. What I mean is, in narrowband concepts, we never bother by this because we give the sine form. Output is also a sine form. In fact, that is a cosine form because lack of phase reference, we won't distinguish between sine and cos. So it was never a problem in narrowband case. In UWB case, yes, it is a very, very important parameter. I will show you some examples how these are going to affect our real applications. The next thing is pulse velocity or group velocity. Quite often in narrowband case, we say that our pulse is PEM wave, hence it should propagate with the speed of light. That's the taken for granted concept. That's not real. We want to see what exactly happens in case of ultra wideband antenna radiation or pulse radiation. And another parameter I would like to discuss with you is pulse amplitude variation. If you see the frequency domain concept, Friis transmission equation, we say how the power of the signal varies as a distance. You may see some surprising results and facts in the time domain compared in that aspect. So overall, we are going to see in this talk how we are going to analyze UWB antennas. As I said, they are very important parameters. And how do near field radiated pulse looks like? What should be the condition for far fields? With respect to narrowband, if you see 2d squared by lambda, we say d is the largest dimension of the antenna. That's how we say. However, in the time for actual time domain, the concept is totally different. We don't have lambda concept here. We will see those aspects in a short while. Okay, just let me give you the background information to develop time domain radiation integrals. Okay, we know that if we know source currents, be it electric current or magnetic currents, generally we use magnetic currents in the case of aperture antennas. Using direct sources, for example, if we use radiation integrals, instead of using sources directly to compute the radiated field E and H, what we will do is we define intermediary functions called auxiliary potential functions A and F. A we call magnetic vector potential and F is called electric vector potential. That I briefly said some time ago. Apart from these auxiliary potential functions, we have another set of potential functions called Hertz potentials. In fact, Hertz potentials were older than auxiliary potential. Somehow, this didn't click to the antenna community. The reason is we were never interested to analyze time domain aspect. All we do is time harmonic case we will take, and we simplify our time variation as e power j omega t. Hence, we get lot of mathematical advantage. So I think now our students are not really aware of what are the Hertz potentials, how they are related to these auxiliary potentials and all. Okay, we have rich literature here. I'm not saying that we are introducing them here. We have very good literature. And today I'm going to consider Hertz potentials to develop these time domain solutions. Okay, as a simple case, we will take infinitesimally small dipole for all possible approximations. That's how we start our radiation, right? Then we expand the antenna radiation problem by constructing as an array of these small dipoles. For example, we have a dipole, and dipole means it is going to have a dipole moment. As soon as we know there is a time varying dipole moment, we expect it is going to have radiation, means it is going to generate electric and magnetic fields. Whereas in frequency domain, the way we will see is time varying current is good enough, means these are two are related as shown here. The current and dipole moment are related to each other. If you take the analogy of time varying current, how we defined A and F, from there how we developed the wave equation, then we find the solutions. From A and F value, we computed E and H. In the same parallelly, we can go here using this equation, we will find out pi e. Once we have pi e, we can find out E and H here. Okay. Let me show you a simple case here. For if we solve those equations, our electric and magnetic fields are going to look like here. You could take analogy again with frequency domain analysis. Here we have a component, electric field component in the elevation plane, and this is the radial component. And for magnetic fields, we have azimuthal component. Same thing is in the frequency domain as well. Here, I want to bring your attention to the following facts. Now, let's say we analyze our problem theta equal to 90. That is the plane perpendicular to the antenna. Then sine theta becomes 1, cos theta goes to 0. First, we will evaluate the magnetic fields. We will evaluate the electric fields, and the same thing can be said about magnetic fields as well. If you see here, I use t hat, which is nothing but retarded time, t minus r by c naught. R is the distance from the antenna. From this equation, we could say that the radiated field is a superposition of three different waves. Let's call them E1, E2, and E3. If I need to evaluate the radiated pulse at a given time and space, all I need to do is compute E1, E2, E3 and add them on the time scale. That's what I need to do. Okay, here if you see, the radiated pulse is a superposition of three waves like E1, E2, E3. If we focus on the how they are varying as a function of distance, if you see, r square and multiplies with r. So E1 term is varying as 1 by r cube. If we focus on the E2 term, it is r square. Here there is no r term here. Therefore, E2 is varying as 1 by r square. And E3, because in the numerator here we have one r, and the denominator we have r square. Therefore, E3 is going to vary as 1 by r. Why I'm focusing on this point is, as we move away from the antenna, E1, E2, E3 attenuates or die off at a different rate. Eventually, when you go further and further, E3 terms remain in the radiation, E1 and E2 get cancelled out or die off. If you are very close to the antenna, E1 is going to dominate. Later, after further distance, E2 is going to dominate. That's why I'm bringing to discussing this and bringing to your attention. Okay, let's take a simple case here. We excite our antenna with a Gaussian pulse, because in UWB applications, quite often we use Gaussian pulses as a source signals. The reason is we could easily define, get the Gaussian pulses using PN junctions, means SRD diodes, tunneling diodes, avalanche diodes, these kind of circuits can easily produce Gaussian pulses. For that reason, we pick Gaussian signals as the source signals. Okay, another thing is, we know that Gaussian pulse has a DC content. Antenna won't radiate a DC content. For that reason, people like to use higher order Gaussian functions. Let's say we take our excitation current is the first derivative Gaussian. Means you could expect one lobe on the upper side, another lobe on the lower side. The effective DC value is 0. Okay, if we compute E1, E2, E3 for the first derivative Gaussian current excitation, our E1, E2, E3 looks like this. Our radiated pulse is a superposition or some superposition of E1, E2, and E3. Now, I will define the Gaussian pulse and I will show you how E1, E2, E3 are going to vary in terms of space and time. Okay, here my selected input pulse is the first derivative Gaussian pulse of minus 20 dB bandwidth is 6 gigahertz. For this current excitation, our dipole would be a Gaussian pulse. P would be a Gaussian pulse. Hence, current would be a first derivative Gaussian pulse, as we shown in the previous slide. The first term E1 is shown here in the blue line here. The E2 is shown in the red line. E3 is like this. Now if we want to find the radiated pulse at a given distance, means I have to sum up E1, E2, E3 at that location. Let me show you how our radiated pulse is going to change. At 1 millimeter, immediately from the antenna, 1 millimeter is a very short distance. Our total pulse is dominated by E1 term, hence it is going to appear as a Gaussian pulse. At r equal to 15 millimeters, this is how the pulse is going to look. As we move away from the antenna, pulse shape has started changing. Very close to the antenna, pulse shape look like this. As we are moving away, the pulse shape is changing like this. Eventually, when you move away 100 millimeters or 10 centimeter away from this infinitesimal dipole, our pulse shape has changed. We have to note this is going to happen whether we like it or not. As we move away from the antenna, the radiated pulse shape is going to change. It will change to some extent or in the distance, then it will be stabilized. Let's say if I move anything above 150 millimeters, 200, 300, now pulse shape is not going to change. It is going to look like the second derivative Gaussian pulse. This is a second derivative Gaussian shape. Okay, this we have to understand. Why this has happened? This happened because of the superposition of E1, E2, E3. So what happened there? E1, E2, E3 varies at a different rate with function of distance. Therefore, this shape change occurred. Another very interesting thing, which you don't want to believe, I'm sure, is this. Pulse speed is superluminal within 10 centimeter and luminal thereafter. I want to take your attention here. What does it mean, superluminal? This axis, vertical axis, is already showing you it is group velocity by C0. C0 is the speed of light. So here, if you see, of course, it is a theoretical analysis. I will talk about experimental as well. The speed of the pulse very close to the antenna is almost 6 times higher than speed of the light. It may sound stupidity, right? How come Einstein can be wrong or causality can be wrong? Okay, no need to worry here. I will explain why this is happening. At the same time, it satisfies the causality condition. Okay, for a second, we will come back from the time domain analysis to the frequency domain analysis. I would like to bring to your attention that near fields, reactive near fields, let's say, and far fields, we know very much. In the near fields, we always say our near fields and the source are in phase. What does it mean is when the source signal goes to the peak, our field strength goes to the peak. When source signal goes to 0, our near fields also goes to 0. That's what we say, they are in phase. We know that. And we say that they are static in behavior because they terminate on the positive and the negative charges on the arms of the dipole. This is very well-known concept. I'm not saying something new here. We are taking the perspective. That's why I'm bringing it here. Once in the very close to the antenna, we have the reactive near fields as well as propagating far field with interacting with each other. As we move away from it, near fields die off, only propagating far fields dominant, and they move in a plane wave configuration. However, this is the point I would like to bring to your attention. When we write the phase in the far field, we write kr minus pi by 2. Clear? R is the distance from the antenna, k is the wave number. Now, if wave propagated r distance of 2 pi by lambda is its phase constant, the phase should be kr. But in our equations, we show kr minus pi by 2. What exactly it is telling us? From where this mismatch is coming? That mismatch is accounted through the superluminal propagation. In this region, if you see where near fields and far fields are interacting, actually the signal speed would be very high. Its phase velocity, group velocity, both are superluminal. In the literature, in some of our papers, we have discussed in thoroughly the derivations, everything. If interested researchers can look into them, or they can contact me if they are interested in conducting the research here. So even though it is very surprising, the signal is superluminal, but it is a fact. Even experimentally also, we measured that. Okay. If I summarize what we observed in the last few slides, the following. Pulse is deforming, means pulse shape is changing due to the superposition of various terms. Those are E1, E2, E3. Because which changes the shape, okay, closer to the antenna with respect to distance. The speed of the radiated pulse exhibits superluminal, that is faster than the light, even though individual terms are luminal. Means if I talk about E1 alone, E1 is always luminal. It is not going to be faster than light. E2, same. It is never going to exceed the speed of light. E3, similar. However, when these three are put together, the pulse formation is becoming superluminal. Okay, here we could say that superluminality is due to the pulse reshaping and does not violate the principles of causality. With the distance, some of the terms of the radiated field attenuates faster and only 1 by r term remains. That is, E3 terms only remains. Hence, in the far field, the pulse shape is stable and luminal. Means it is nothing to worry in the far field. Okay, now simple dipole we explained. How do we extend this analysis for different antennas? Here we can, okay, if we like, we can use numerical techniques. No problem. To explain, to demonstrate the physics, I would like to go by simple method, that is Huygens principle. In Huygens principle, we know that every point on a wavefront is a source for the next wavefront, right? Okay. Let's say this is a ridge horn antenna. This is the aperture where electric fields would be. Based on the ridge dimensions and mode of excitation, generally we go by dominant mode, TE10 mode. We should know how the electric fields vary in the aperture. Now, if we take this as a primary wavefront, every point on this wavefront acts as a source for the next wavefront. Based on the field strength and the time delay they arrives onto the spot, we could define number of infinitesimal small dipoles with a proper excitation. Here you could see in the right side figure. These red dots are the locations where I consider my dipole is present with a proper excitation. What it means is at the center, the field strength is going to be very strong. Therefore, excitation for the center dipoles would be much higher, whereas for the edge ones, very lower, because this is electric conductors. Here we could say E tangential is 0. Therefore, the field strength goes to 0 here according to the boundary condition. This is the field variation you could expect. However, due to these ridges, more concentration would be there. That could be explained as a cos power of 6 or 7. That varies with the dimensions of the ridge. Once we have the field aperture fields, now we could develop the radiation from these kind of antennas in time domain. Let me take one of the antennas available in our lab. Just is a pyramidal horn antenna. And TE10 mode is the excitation. The waveguide dimensions, feeding dimensions, and aperture dimensions are given here. Now we fed Gaussian modulated sine to this, and we measured the radiated pulse at various locations, and we evaluated the shape and measured the speed of the pulse, how much fast the pulse is propagating. Okay, here is the waveform predicted. Predicted means by modeling the way we discussed it so far. And experimental, we actually measured using another antenna. And see clearly up to let's say 1.35 nanoseconds, up to this region, our accuracy was quite good. Later, they fall apart, but if you see the strength of the signal is so weak compared to the main signal. And whereas the speed of the pulses, if you see, this is the pulse peak. If you track the pulse, how fast it is moving, this is how the speed is. Here you could say, let's say roughly 1 centimeter from the antenna, this is approximately 1.75 times C. The pulse, this peak, is moving at this rate. And sometimes we use pulse envelope as well. Envelope is nothing but by using Hilbert transformation, we add pulse and Hilbert transform with the J term, then it will give you the envelope. In imaging and radar applications, quite often we go for envelopes to avoid the noise and all. Even in that case, it is superluminal. This region, you could see it is superluminal at a distance 1 centimeter. We could see what happens with Vivaldi antenna. This is a Vivaldi antenna whose bandwidth is 1 to 11 gigahertz. These are the dimensions. We know that it is a simple traveling wave antenna. Electric field will be supported by these two leaves. As the wave moves forward, the coupling between these leaves and waves will be weaker and weaker. Eventually, it detaches into the space. Now, if you go and measure the radiated pulse or analyze the radiated pulse, this is how it is going to look like for first derivative Gaussian pulse. See, very close to the antenna, it is more like a first derivative, but small distortion. As you go away from the antenna 10 centimeter, 20 centimeter, 30 centimeter, 35 centimeters, it is becoming a proper second derivative Gaussian pulse. Do you remember in the radiation E1, E2, E3 terms, by the time we reaches to about 20 centimeter, E1 and E2 died off. Only E3 remained. That's why we are looking like a first derivative Gaussian pulse. And another interesting thing is the bottom graph. If you see here, this is the pulse speed in various directions. This is the one that is really spoiling entire game. If you take a radar imaging, localization, ranging, or any applications, the problems are coming because of this behavior of the antenna. In 90 degrees, this is the 90 degrees, this is 0 and 180 for this antenna. Very close to the antenna, yes, it is superluminal. As you move, it becomes luminality. If you go to the extreme cases, either 0 degrees or 90 degrees side, the speed of the pulse is really high, even exceeding 10 times the speed of light, the peak. Okay, this I will discuss in detail in a short while. Just take note of this property. In frequency domain analysis, we never go here and discuss these. Those are the issues. All our research, I think we need a solid research to focus in understanding these phenomena and correct them. And this analysis we did for other antennas, those kind of properties are persisted here. In terms of pulse radiation, pulse shape change, we accept, yeah, in the near field it change. As long as you are in the far field, pulse is more stable, no need to worry. The biggest challenge is the speed at which these pulses are moving in an angular. In bore site, you have one speed. If you go off the bore site, the pulse speed is changing. Those are the dangerous features. And monopoles, still it is a unsymmetric behavior as well. This could be a reason that monopoles, we don't have proper surface current distribution. Somehow they're giving you impedance bandwidth, but in reality, for UWB radiation, they are really miserable. They are not good. Maybe we have to find new techniques how to correct it. Okay, I want to demonstrate this effect even more thoroughly by considering reflector antennas. A simple reflector I take. We know that dish antennas in India, we quite often we see everywhere. There would be a feed horn, there would be a reflecting surface. When we illuminate the reflecting surface, surface currents will form and those currents re-radiate, and you get, based on the reflector size, dish size, you can have really high gain antennas, 40 dB gain, 50 dB gain also possible, right? Even sometimes we could synthesize this array using a square kilometer antennas to have a pencil beams for radio telescopy and all. We use those antennas. We know that even over the horizon radars, etc. Okay, now we'll come back to UWB stuff, and I would like to describe this for two reasons. One, as an antenna, two, as a reflector, as a target in radar case. Once we illuminate this surface, I have taken 28 centimeter by 28 planar surface. I use a feeding antenna, which is a transmitter, Vivaldi antenna, and I have another receiving antenna where I can move to different locations and measure the radiated pulse shape and then speed. This is the typical radiation pattern of our Vivaldi antenna. This is illuminating this surface. Based on the field strength, this is how the surface currents are going to form. Okay, as expected, in the center it would be strong currents. As you move away, the current density will, and the antenna is in vertical, and this antenna has a good cross pole. Therefore, you see very strong currents in a vertical direction. No need to worry. So far, so good. Now, I'm going to consider these currents as a small dipoles radiating back, as shown here. Okay, my input pulse to the feed Vivaldi antenna is the first derivative Gaussian pulse. This antenna illuminate this, and illuminate means I give first derivative Gaussian pulse. When the signal comes out of this transmitting antenna, because of the effect which we taught, it already changes its shape to the second derivative. One more time derivative happens. Okay, now the second derivative pulse hit this metal sheet and induces the currents. Now those currents we take as an array, and we projected the reflected fields from this planar array. These are the measured and predicted pulses. At 7 centimeter from the plane, this is more like a second derivative Gaussian pulse, right? And as we move distance 45 centimeter, already shape changing, shape formation, deformation occurred. For 60 centimeter, even deformation occurred. For 100 centimeter, it became like third derivative Gaussian pulse. See, this pulse at 7 centimeter, by the time you reaches to 100 centimeters, the time derivative already occurred. This is because E1 and E2 got died off and E3 remained. Now, another interesting thing is how the speed of the pulse. Okay, before I go to the speed, I want to show you the full picture of the measured pulses. I measured at 5 centimeter. It is like a true second derivative Gaussian. Means it is exactly like the incident pulse it appeared. If I could able to go 1 centimeter or within 1 centimeter, perhaps I would have seen the incident integral form of it. However, I couldn't able to go too close to that in the measurement. So we started from 5 centimeters. So this is how the pulse shape change occurred. From 5 centimeters to 130 centimeter, second derivative Gaussian pulse to third derivative Gaussian pulse occur. If we go further away from 130 from the reflector, the pulse shape won't change. It would be fixed. Now I would like to show you the pulse peak velocity, how the pulse peak is changing. This is how. Let's say at very close, it is almost like a 2 point, yeah, experimental and predicted. We take a lot of pain to go to such an extent and really pick the peak. And it's not exactly 2.5, very close to the 2.5 times the speed of light. As you go after, let's say 35 centimeter or so, it became luminal. It means after before, if we do any experimentation or you develop any application within 30 centimeter from this, if we apply the regular concepts, the speed of light is c naught in the medium c by square root of epsilon r, we write. If it is a free space, we simply say c 3 into 10 power 8. In the initially, we didn't understand why everything is distorted. When we are developing the images in the near field, we couldn't able to get quality images. Then we thought, first we are doing the mistake. Then we start doing the analysis. Then we realized this phenomena is indeed real. Later, I'm going to show you some applications and demonstrate how they are going to affect our real experiments. Okay, here if we see observations, I'm again kind of summarizing. The pulse shape changes. The coherent addition of these E1 to E3 forms the radiated pulse. Changing the pulse shape make the pulse shape travel faster than light. Once the, these two are the points. First 2 points we already covered. Once the pulse reaches the far field, the contribution from the first 2 terms becomes negligible and the pulse shape ceases to change and becomes stable. Hence, in the far field, pulse shape is stable and travels with the speed of light and amplitude varies linearly with the distance. This is not the case in frequency domain. In frequency domain, we will say that it will vary frequency doubles, your attenuation becomes 4 times square term, right? That's not the case in UWB case. Okay, now I will talk about more on far field distance. How do we define far field distance for UWB antennas? Sure, previously we said 2d square by lambda. When we define 2d square by lambda in the frequency domain, the phase tolerance we accepted was 22.5 degrees. It means if you go 2d square by lambda away from the antenna and you draw a horizontal line, if you measure the phase variation across that, it won't exceed more than 22.5. That's what it means, right? Okay. Now, far field distance here, how do we should define far field for UWB antennas? Based on the radiation characteristics we studied, in the far field, pulse shapes should be stable. It means a derivative should occur for the input pulse. Second, pulse speed should be luminal. It means pulse speed should be equal to C naught. And third characteristic is pulse amplitude variation should be 1 by R. Okay, now if we see that in comparison with narrowband condition, far field for UWB antennas occurs much shorter distance than narrowband condition. It means I don't need to go 2d square by lambda distance to achieve these 3 characteristics: pulse shape stability, luminality, and pulse amplitude variation as 1 by R. And this is the point I was mentioning previously. UWB antenna radiation is non-synchronous. This is really bothering us. That is, radiated pulse reaches different distances in a given time in different directions. For most antennas, pulse speed is lower in the bore side direction and maximum in the off bore side direction, means even perpendicular to the bore side. Okay, most antennas radiated pulse is the time derivative of the input pulse. And special cases are here. Radiation from a long continuous radiating structure. Suppose if we have a long wire and pulse is propagating along the wire and it is continuously radiating. In that case, our radiated pulse is a summation or integration of various sections of the pulse radiation, or pulses radiating from various sections. Therefore, again, you will see integral effect. Okay. This one we seldom see, and we generally in our antennas it won't happen. This is for the case of transmission lines. So we are not going to pay much attention how to calibrate that and all. Okay, as a summary, as a takeaway point at this point of our talk, I would like to say this. in the far field, three conditions should be met. One, radiated pulse should be stable. Radiated pulse should propagate with the speed of light, and pulse should vary as 1 by r. If you observe these three characteristics of the radiated pulse, you can call it is in the far field already. Okay, so far we talked about how the antennas behave in the transmitting mode. So now we will throw a light on how these antennas behave in a receiving mode. According to Rayleigh-Carson reciprocity theorem, we could show that there is a paper by M. Kanda. The transmitting transient response, let me read this one statement. The transmitting transient response of an antenna is simply the time derivative of its receiving transient response. And this is for a far field only. It means we know that if you give, let's say, a particular signal S of t to the antenna, when it radiates and goes to the far field, it becomes d by dt of S of t, means time derivative of S of t. According to this definition, if you put a receiving antenna there, it should not alter while receiving the pulse, because already transmitted transient is having time derivative. According to this definition, if let's say we take a transmitting transient as a reference, our receiving transient should be integral of transmitting transient. Therefore, already time derivative occurred in the transmission. Therefore, in reception, nothing will happen. Just it will take the pulse. Therefore, if you put two antennas face to face in the far field and you give a signal to the transmitting antenna, finally your received signal on your sampling oscilloscope or your UWB receiver is going to be one-time time derivative of the input pulse. Okay. And we know that because of this fact, UWB antennas are non-reciprocal. Whereas in narrowband case, we take them as a reciprocal because we won't distinguish between sine and cosine when the phase is not there was no phase reference. Now, I would like to show you what kind of effects this superluminality or means a time insynchronicity, non-synchronous time behavior is causing us. Here, I consider 3-point targets. The dark line, dots shown here are the 3 targets. My goal is to locate them, image them, and have the measurement done. Means the distance I want to measure. So I have set of receivers, or one transceiver goes along the circular path using synthetic aperture radar concept. I collect the data and I created the image. In this image, I consider speed of the signal as C0. Conventionally, that is how we go. And these targets are close to these antennas, so they are not truly in the far field. What happened, we notice. Instead of 3 targets, I am seeing 2 dark actually, the green stars I have shown here, I expect the target should appear here. No, they move to this location and this location, and kind of I missed this target overall. If I go by just conventional assumption of signal is traveling with the speed of light, I would clearly wrongly I would judge where the targets are. So I corrected back in the signal processing by taking the superluminal speeds, and I could able to reconstruct the image there, get back to the actual dimensions. Even this can be shown in various applications. Suppose when we are checking holes in a pipe or in a sheet, we could see that we will have a row of sensors will be moving along the path and to automate the checking process. If I take this just a conventional assumption, and this is how image is formed. If you see, the energy distribution in the reconstructed image is not fine enough. Moreover, it slide to almost 5 millimeter position, means aperture edge is showing that 5 millimeters away. However, in reality, we have 1.62 centimeters away. After correcting this superluminality concept, I could come very close to the actual value. So through this, I could demonstrate how these are affecting us. In a regular applications where dimensions are not that critical, now we are talking millimeter or sub-centimeter accuracies. In those cases, these superluminality or time, synchronous, non-synchronous radiation is causing the problems. Here I want to show you biomedical application problem. You heard about, there is a intense efforts are going on to develop microwave imaging system for breast tumor diagnosis problems because these are non-ionizing waves. X-rays are ionizing and causing the side effects, especially young patients. So to develop a system for this, first we built a prototype 3D printed breast model developed based on MRI images. The image which this is the prototype model using PTFE plastics. We developed this breast model. Inside is the fibrogranular tissue and outside is the adipose tissue regions. To mimic this phantom close to the human electrical properties, we filled with liquids, Triton X100 and deionized water in various compositions. This is the cross section where I want to image. And if we go here and see, this is how the actual photo supposed to look like. Okay, now I'm going to show you. Okay, I'll come back to this slide. First, show the results and I will come back here. Then it will be more helpful. Okay, whatever you are seeing is this left side image is generated based on radar imaging. Here we use the 7 gigahertz bandwidth, and this is MRI image of that phantom, 3 Tesla MRI image. Okay, this is the tumor we incorporated, and here also it has clearly shown this is 1 cubic centimeter of the tumor filled with epsilon r of 42, and whereas the surrounding tissue epsilon r is 36. This fibrogranular tissue region is 36, adipose tissue was 5 epsilon r. Okay, we know that the image depends on the contrast between the target and neighboring tissue. Very good. Here the contrast is not that high. If the tissue forms in the fibrogranular tissue region, the contrast won't be so high. Okay, here what I want to say is, when I created the image with taking the superluminality effect into the consideration and section by section, I could come up with as close as possible to the 3 Tesla MRI image. I won't say that we ever going to beat, microwave imaging is going to beat MRI, but it is very close. That's what I would like to say, that if you take care of everything, we can improve the performance of the systems. Okay, now I'll come back to the slide which I said. This is how electromagnetic pulse is hitting the tumor. First, there would be a matching liquid, is a vegetable oil we use, epsilon r3. Then it impinges on the adipose tissue, epsilon r is 5. There is a reflection generated here. Then if you see here, epsilon r changing, hence the group velocity is also going to change. If we are not able to capture the group velocity properly, either we enlarge a particular region or shrunk the region, image proportion will get affected. For that, we need to have a good understanding of at what speed the pulses are propagating. That's what I mean to say the importance. Okay, now come back to the actual antenna, what we want to do in future, etc. Okay, what should be the ideal characteristics for UWB antenna? For example, as I said, radiation stability should be there. In all angular positions, antenna should have the stable pulse shape, and Time synchronous radiation is the next one. Okay, ideal UWB antenna should be able to radiate pulse in the same way in all the directions in terms of pulse shape stability and pulse synchronization. It means pulses should travel the same distance in all the directions for a given time. Otherwise, it is going to be difficulty. As we previously said, right? How the effect is going to have. To some extent, these shortcomings can be accommodated through signal processing. However, the load on the system is going to be real bad. So I'm going to take Vivaldi antenna as a case study, and I want to go in detail what we can do to improve the antenna characteristics, how we narrate one by one features. Many of you might have already designed Vivaldi antenna, or you might have used it, or you might have published a paper also on it. It's a great antenna. Vivaldi antennas are more popular for UWB applications, no doubt. They have excellent bandwidth, return loss, gain, and pattern stability, etc. Now the question is it makes a good UWB antenna? How about radiated pulse stability in different angular positions? Can it provide time synchronous radiation? What about pulse distortion? I'm going to discuss these details. Here, I'm going to show you, I take the simple Vivaldi antenna in the E-plane, 20 centimeters from the reference point. Typically, we take edge of the antenna as a reference point for all applications, right? This waveform, the bottom waveform, is going to look like how the pulse shape is going to look like, radiated pulse shape, and at what time it reaches the 20 centimeters point. This is the input, is more closer to the first derivative Gaussian. This you could clearly see, it is a second derivative Gaussian. Clearly, we are in the far field. As same distance, 20 centimeter in 20 degrees position, 40 degrees position, 60 degrees, and 90 degrees. See the pulse shape change. Here it is quite good. It's not bad. It's also okay. I will also go with it. See here, pulse shape has distorted. That is not bothering me compared to the following. See the time. In the bore site, it took just above 1.5 nanoseconds time to reach 20 centimeter. Whereas here, it is less. The difference between, the time difference between this pulse and this pulse is 77 picoseconds. It means the pulse is reaching 20 centimeter distance here, 77 picoseconds before the pulse reaching in the bore site. If we want to have a great imaging application using microwaves, you have to take care of all these. So our imaging algorithm, our signal processing, our data conditioning are going to be extensively expensive because of this. Even it is exhausted, even enhanced in the E-plane, H-plane case. Here you see the same. Here the difference is 251 picoseconds. How to correct it? Can we able to correct it? Is there any methods available? Or as of now, I haven't seen any literature. In my opinion, this makes a good research topic because it is very important for radar applications or other applications. Okay, here I would like to summarize what we noticed here. Even though the radiated pulse shape is stable and acceptable, but needs improvement in pulse synchronization. These characteristics can be explained through the phase center of the antenna. The phase center is an apparent point on the antenna where it appears the radiation starts at a given frequency. Sometimes the phase center can be outside of the antenna structure as well. By controlling the surface currents on the antenna, it is possible to shift the phase center of the antenna for a given frequency. We know quite often we use or manipulate surface currents to miniaturize the antenna. We cut the grooves, we allow the currents to go over a longer surfaces or longer paths so that the frequency comes down. Yes, if we have strategically or if we somehow we could able to control the phase center of the antenna by controlling the surface currents. Obviously, surface currents are source of radiation, we know that. Through that, we may able to achieve a better characteristics for the antennas. Let me show you here the phase center study on a Vivaldi antenna. This is a regular Vivaldi antenna whose bandwidth is 2.5 gigahertz to almost 11 gigahertz impedance bandwidth. Great. If I see the phase center, okay, maybe I would draw to your attention. This is the antenna structure which we posed here. Okay, this is the reference point if we take for 2 point almost close to 2.8 gigahertz, our phase center is here. Means it appears that 2.8 gigahertz signal, if we see the frequency domain analysis, it is going to radiate from this edge, from this location. As the frequency increases, the phase center is moving towards the into the inside of the antenna. It is rightly so. As I said in the beginning, it is a traveling wave antenna. Electromagnetic wave is supported by these two leaves, the coupling, right? Low frequencies as higher lambda wavelength, so they can easily hang on to the structure till the end. Whereas higher frequencies, shorter wavelength, they easily detach from the inner side itself because they weakly couples to the structure. So as the physics suggested that the frequency increases means the phase center will go inside. Now the question is, after this 4.4 gigahertz, where the phase center is going? It is going to the out of the antenna. That's the problem is really bothering us. Is there any way or can we do some research and somehow able to bring it to the finite location? Let's see, we put some effort, but we didn't master the technique yet. We are also did not understand thoroughly yet. We are working. Maybe you guys also interested can take this research further by studying this. Okay, we cut the grooves as shown here, and we optimized also a little bit of this shape for the miniature. Otherwise, the size is going to be too big. Yes, as you guys expected, the operating frequency moved lower and our phase center is also improved. Here I'm showing you the phase variation at two locations, 90 degree away. One is bore site, another is 90 degrees away from this, which is perpendicular to the bore site. At 3.5 centimeter inside from the edge, when I go inside 3.5, the phase center is like this. Between, I say, 1.5 gigahertz to almost 4 gigahertz, we have the same phase. It means the phase difference or the speed at which the signals traveling either in the bore site, in the off bore site, is more or less same at the between 1.5 to 4 gigahertz. Now, if I see the time domain effect of this antenna, this is okay. Before I go to time domain effect, I will show the near field superluminality of the pulse. Very close to the antenna, the speed is 1.12 times. As I move away by 10 centimeter, kind of 12 centimeter, we hit the far field. So here is the time synchronous radiation we are expecting. This is the bore site, the bottom line, and this is 90 degrees away, which is perpendicular to the bore site line. Compared to the previous case, the time difference between these peaks is shorter. Now, still I have the difference. Previously, we have seen 77 picoseconds in the E-plane, whereas here I'm seeing only 27 picoseconds. So kind of 50 picoseconds has been covered, but still there. In my opinion, okay, let's conclude what we have discussed today here. In my opinion, we need more research efforts to understand the time domain radiation and reception of radiation and reception of UWB antennas. UWB antenna design should consider not only just frequency, operating frequency and gain, the pulse stability, time synchronized radiation we want to see. In my understanding, still we have a strong demand for UWB antennas for radar and communication applications. For example, radar imaging is really extending now. From earlier ground penetrating radars are just shows the waveform. Nowadays, we are giving centimeter accuracy imaging for a shorter depths though. So the interested frequencies for radar imaging applications varies from 0.5 gigahertz onwards up to 6 gigahertz or even 8 gigahertz also there. If we have a good UWB antenna working from 0.5 gigahertz to 6 gigahertz, I am ready to buy. I can pay for this antenna. And similarly, 5G communication systems. We need UWB antennas, especially for high-speed trains. We know that aerodynamics is also very important for high-speed trains. Not only electrical properties, mechanical properties are also very important. This is what I believe future for UWB antennas. So I'm stop sharing my screen and I open for the question answers. And yeah, let's see how you people felt it.
Any questions from the participant side you can ask?
Yeah, it
Any
seems there
questions
is a
from the
question.
participant side?
Hello, good morning, sir.
Yeah, good morning.
Sir, my name is Brij Kumar Bharti.
Yeah.
Sir, I want to ask how can I measure fidelity factor for UWB antenna?
Okay. Fidelity. First, we want to define fidelity factor. Between which two pulses you want to measure the fidelity factor?
Yes, sir,
Let's.
transmitted one is from transmitting antenna
Ah,
and what we receive at receiving antenna.
ah. So fidelity factor you are measuring between the input pulse and the received pulse, isn't it?
Sir, yes, sir.
So what are you expecting here? Now we have shown ideally the received pulse is going to be the time derivative of the input pulse. You should not expect your same pulse shape appears at receiver, right?
Yes, sir. Yes.
Okay, few things here. Suppose you already take theoretical time derivative and you compare your received pulse fidelity factor. Basically is a measure of how similar these two are.
Yes, sir. Yes.
Yeah, correlation function, or in the literature, if you take couple of people define differently, taking the product square and etc. Even at the end of this presentation, I gave some of the reading material. There it is defined. In my opinion, what we need to understand is between what two pulses we are taking the fidelity factor. Fidelity factor is a measure of how well your antenna is doing its job. In the literature, I'm seeing some researchers are taking the input pulse and the received pulse and trying to do the fidelity factor. Here, that fidelity factor won't make sense at all. In our analysis or whatever we have shown, you have to, if at all you want to consider the fidelity factor, you have to take the fidelity factor between received pulse and the time derivative of the input pulse.
Okay, sir. But how I can measure this? By
As I
using
said,
like HFSS, CST, or how can I can measure it in MATLAB?
for time domain, CST is very good. Or you could take into MATLAB and just compute analytically.
Sir, is it possible to measure it in HFSS?
Once you have the pulse shape done, yes, you could do. Myself never uses the HFSS for these simulations. My students use CST most of the time.
Okay, sir. Thank you, sir.
Yeah.
Any other doubts? You're welcome to ask the doubts.
Yeah, there is a
Yes.
hand to Ramya.
Good morning, sir.
Good morning, Ramya.
Sir, fidelity factor can we measure fidelity factor from the CST software directly, sir?
The way we are
Otherwise-
measuring is we take the pulses and we use MATLAB function to
Calculate.
compute that. Yeah,
Thank you, sir. Thank you.
yeah.
Sir, I have one question.
Yeah, sure.
May I ask?
Yeah.
So you
Rishi is
talk
talking, right?
about this. Yes, sir. Yes, sir.
Yeah,
Rishi
Rishi.
over here.
Yeah, Rishi.
So I was asking this superluminarity concept you taught us.
Yeah.
So theoretically, you said that it is 6 times.
No, that is for infinitesimally small dipole.
Okay. And
It
the
depends
practical
on
one.
the antenna aperture.
Okay, sir.
Yeah.
So experimented was 2.5 times, and for infinitesimal dipole.
Yeah,
it was
as I
6
said, we
theoretical.
did experiments with miniaturized Vivaldi antennas, horn antennas, and reflector array antennas, means reflector antennas basically, where it
Okay, sir.
varied from 1.2 to 1.25. The major effect is when I think I forwarded the slides to Gautam. There I gave some of the reference papers or study material in case somebody interested.
So, yes, sir.
So you could see them in various experiments, how we used and all. Or if
Sure,
anybody
sir.
contacts me, I can also send some of the literature.
Okay, sir. Any more doubts from the participant side? You can ask.
Yeah, there is a
So
question.
I think
No, there is a question from Sachin.
Okay, Sachin, you can ask.
Hello, Sachin.
Yeah, Muthuramaya, you raise your hand. So please ask.
He has asked already, sir. Sachin, sir, you have any doubt? You can ask. Participants, any doubts? Please ask. Sir has delivered an excellent session on ultra wideband antennas. If you have any doubts, you can ask.
Yeah, I believe many of you are doing research on UWB antennas. In case you want to have collaboration or you want to have any discussion with me, you are welcome, either through Gautam or directly to me.
Gautam, sir, your mic is mute.
Yes, Nipun. Yes. You want anything? Yes.
Yeah,
Yes, please
Nipun.
ask. Nipun.
Nipun, your microphone is muted. Yeah, now you could speak.
Sir, can you explain the working of this Vivaldi antenna?
Working principle of the Vivaldi antenna?
Yeah.
Okay.
And
Let's
how-
say, sorry?
Yes. No, sorry. Just go ahead.
Yeah, if we see the structure of the Vivaldi antenna, there would be a parallel lines in the beginning at the input feed. As the structure moves forward, slowly these two lines displace from each other, and the gap between these leaves we call gradually increases. The basic idea here is we are able to transfer the electrical signal from the transmission line. Initially, it is a simple TEM transmission line. As it moves forward, we are altering its pattern or configuration, field configuration. Between initially it was vertically down. As you move towards the edge of the antenna, the electric fields shares between top leaf and bottom leaf. As the wave propagates down the wave, they becomes weakly coupled. The energy would be weakly coupled to these leaves. Once you taper down, if you see the edge, it will go and turn like this. At the time, the energy coupled to this weak, you could analyze the way the dipole radiation occurs when the signal goes to the zero. At the time, they forms the band. Do you remember how we study the
Yes, sir.
dipole radiation detachment?
Yes, sir. Yes, sir.
When the signal goes to zero, basically due to the property of electromagnetics, the initially electric lines of force are supported by the charges on the dipole arms. As the signal momentarily goes to zero, then they becomes the loop to satisfy the boundary conditions. Similarly, when the wave propagating from the connector towards the end of the Vivaldi antenna, weakly, first strongly coupled, they can't detach into the as a space wave or into the space. As they move towards the edge, the coupling between the leaves, if you see, they are very weakly coupled. Eventually, it leaves and it comes to the end. So what we noticed while studying the phase center is low frequencies are propagating till the end, whereas high frequencies are not even reaching the end of the antenna. Before that, they are leaving the antenna. Nipun, does it make sense to you?
Yes, sir. Yes, sir.
Yeah.
Thank you. Thank you, sir.
Yeah.
Yes, anybody else?
Sachin sir, you want to ask any doubts?
He might not be there.
Okay. He's unmuted his mic, but okay, fine.
Okay, go ahead. No issue.
Sir, there is one more question.
Yeah, sure.
Sir, why this
Go ahead, sir.
monopole structure provide the means very large bandwidth?
Monopole, yes.
Means when we are removing the means we are using the partial ground plane, then
Yeah,
why
yes.
how this monopole provide the very large bandwidth?
The Q factor is going to be too small, isn't it? When we remove the ground plane,
Yes, sir.
the Q factor of, because effective epsilon r, if you take it, is close to the free space. That's why by printing monopole on a high dielectric constant, you won't get miniaturization. So because of the low quality factor in the structure, we get generally high bandwidth.
Please mute yourself. Participant. Chinta, please mute yourself. Okay, please go ahead.
Okay. Monopole without ground plane, even though it will give the frequency bandwidth, but radiation stability will be very poor. It accepts the energy, certainly, because quality factor is so low, it can throw the energy anywhere. But the boundary conditions, if we take a simple boundary condition, means radiation, resonance effect, right? Simple monopole dipoles work based on the resonance condition. At the resonance means we have to have current minimas and vary in between the currents sinusoidally. In case of monopole, if you study the surface currents and all, they would be randomly distributed. Hence, we won't get radiation stability or gain properly. Especially if you see the radiation pattern of a monopole at a higher frequencies, it looks like a zigzag. It means energy is not directed properly.
Okay, sir. Thank you. Thank you very much for nice explanation.
Any other doubts? Any other doubts from the participant side? You can ask.
I think there's no much doubts.
Okay, sir. So I'll conclude the session then. Thank you so much, sir, for sparing your precious time for this FTP occasion.
Thank you, Rishi.
Thank you so much, sir, for guiding us, for giving us such an informative session on this time domain analysis of ultra wideband antennas using Gaussian pulses. Thank you so much, sir.
Thank you, Rishi.
Thank you.
Thank you, Gautam.
Thank you, sir. So I'll send you one mail and please return it back to me.
Yeah.
Thank you very much.
Okay, thank you.
Thank you very much, sir. Thank you. So all the participants, so we have concluded the session. The next session will be at 12 o'clock by Mr. Karthik Goyal from Design Tech System Private Limited. Will be delivering a talk on role of EM simulators, FEKO, in handling electrically large problems. So 30 minutes before the session link will be shared on the WhatsApp. And please do join on time. Thank you all for joining the session, for your patient listening. Thank you all. You can leave the meeting now.
See, off the recording. Okay.
Yes, sir.